All right, and we're live.
Yes. All right. Yeah, I'll propose to wait a bit to have everybody to have the full presentation, of course. So yeah, maybe we'll wait for like 5 more minutes before we start. I can already do like a small intro, maybe. Presentation, of course. So yeah, maybe that was on repeat. Yeah, so I'm very happy to see a lot of interest in this great topic. I think we have around 280 people attending this meetup, so that's quite an amount. Yeah, we have Lak here, who is the head of data analytics and AI solutions at Google, and also the author of this great book, What the Presentation is About, of course. It has been a while since we did a last meetup because we really want to really value the interactions. So as well today, yeah, we have the YouTube channel available to basically ask our questions. So also Lak can answer those questions posted there. And if it's possible, maybe we can do it in both directions. We'll have to figure it out together. And also we have a next meetup to really have like group discussions in closer groups about the book and the different design patterns as a follow-up on this. We already shared it online, and it was already, yeah, everybody's on the waiting list. But if we have a lot of people on the waiting list, we can also do more meetups on this to have more people included in the discussions. So that's basically the idea. So something else to add, I would just say, please ask your questions in chats because we're really looking forward to the discussions as well. And with that.
All right. Thank you very much. Thanks. Shall we get started, or should we wait a couple minutes?
Yeah, I think we can wait 2 more minutes and then we can start the meet.
Absolutely.
So maybe if somebody already can, like, I see it's working. So we have in StreamYard as well the comments popping up. We have a lot of highs.
And we'll see if they show up on StreamYard here in a minute. Oh, I see Cohen. Hi, Cohen.
The highs are popping up, so it's really working. So that's good.
Awesome.
All right.
Good evening. Yes, it's the start of the day for me here. It's one of those rare sunny days in Seattle, so I had to actually close the window. That's why you see the sunlight on my shoulder.
It's getting darker here, so it's yeah, a bit of difference.
Yeah, I think we now have sun past 5 p.m., so that's good. It's getting to be longer days.
All right. So you have enjoying the sunny day that's popping up. I think with that, probably we can start to dive in, and I'll leave you for that.
Okay, thank you very much, Matthias. Hello, everyone. My name is Lak. I lead analytics and AI solutions in Google Cloud. And today I'm going to be talking about a book that we published a few months ago. It's called Machine Learning Design Patterns. And these are my co-authors, Sarah Robinson and Michael Munn. And so what is this book about? Okay, it's basically around what are called design patterns, which for many of you will be familiar from, for example, the Gang of Four design patterns. It's essentially best practices to solve common problems whenever you're designing a software system. And the idea is that there are some things which are so repeatable that we can make it an API, we can make it a library, and we can just go ahead and use it. But there are other things that are more conceptual. And the idea behind the conceptual things is that these are, you want to understand when to use them, where to use them. There are going to be trade-offs associated with it. But these have been proven successful in the past. One of the marks of any software enterprise becoming more mature is that you start to see design patterns crop up that a lot of experienced people know about. But then how do you get the folks who are relatively new to the field to recognize that this is a place where a pattern is useful? Or it's often the case that you may be using a particular pattern, but you may not have, if you don't have a name for it, you're essentially reinventing it every time. And it would be good if we assigned names to things that are familiar enough. And that's the purpose of design patterns. It's to name things so that we basically make it much, much, much easier to reuse them. So in our book, we covered 30 design patterns, and there's a GitHub repository associated with the book, ML design patterns. So ML-design-patterns. If you search ML design patterns on GitHub, you should be able to find it. And this basically has the list of the 30 design patterns that I'm talking about. So some design patterns around data representation, some design patterns around problem representation, and some patterns that basically work to improve like the model training part, and the others that are around resilience. Resilience meaning that you're able to scale, right? You're able to handle many more requests per second, for example, during deployment, or much larger data sets, etc. Right? And then the last but one chapter is on reproducibility, because one of the big issues with machine learning is that we apply a lot of pre-processing operations during training, and the question becomes, how do I make sure that these are perfectly reproduced during prediction? So there's a number of patterns that basically help you with that reproducibility. And then finally, we talk about patterns that help you do AI responsibly. So those are the 30 patterns. And the patterns themselves are, those are the 6 chapters that I talked about. And the patterns themselves are pretty related to each other. So one of the key things is that we say, if you're going to be using feature crosses, you should probably use them with embeddings, because these are related patterns, and embeddings kind of help address some of the drawbacks associated with a feature cross. And many of these patterns are all about addressing 3 kind of areas of challenges in machine learning. The first one, the very important one, is around data quality. Okay, the quality of your ML model is only as good as the data that you use to train it with. And you could have quality problems in the features themselves: measurement errors, recording errors, duplicates, missing features, etc. And that's an interesting point. Why is the duplicate a data quality problem? Well, it becomes a data quality problem because when you have a duplicate in your training data set, that example gets overweighted in relationship to all the other examples. So duplicates are going to actually cause accuracy problems. I mean, you can just imagine at the extreme that you have some sort of situations duplicated such that they become about 30% of the training data set. And at that point, then your entire model is capturing much more effectively the part of your data that's been duplicated, whereas the ones that aren't duplicated are not weighted as highly enough, because duplicates essentially become a weighting mechanism. So that's why duplicates are a data quality problem. You could also have quality problems on the labels, right? Whether the labels are accurate, whether they're consistent. Oftentimes we use a labeling service and different people label the same X-ray differently. Some doctors may call it a fracture and other doctors may not call it a fracture. So how do you deal with that consistency issue? You also have data set completeness issues with machine learning, where you may be capturing only a portion of the of the data that you will actually encounter during production. So you may be missing a few scenarios completely. And then a big problem around accuracy is quality is around timeliness, right? You might be training on data that you assume is going to be present, but it turns out that the feature data is like 3 days delayed. It takes 3 days for the data to actually land in your system, which means that during prediction, you're actually having to predict with older data than you trained with. So timeliness could be a problem. Another big category of problems is around reproducibility. And there's inherent randomness whenever we do machine learning, training, dataset splits, etc. But you also have dependencies on frameworks, right? And maybe you have a different version of the framework, or maybe you've trained your model and you wrote all of your pre-processing code in Python, but then your production system is in Java, and now you have to basically replicate whatever you did in Python in Java as well. And there are differences between the two languages and the two libraries that you're using. So there could be reproducibility problems in the training environment because you are distributing, and some workers get finished before others, and so there's different problems in terms of having the same experiment produce the same results. And then, of course, big problem in ML always is basically making sure that whatever you trained with, you deploy, and it's basically you're deploying the exact same thing. The third category, I'm just combining them, is that you basically have issues with drift. You have issues with scale, large data sets, many queries per second, etc. And then changing in purpose, right? So oftentimes you train a model for one purpose, and then you take that model and you try to do something like transfer learning on it, and you're transferring it to a new problem which isn't quite the same, and that can cause issues as well. You can have problems around objectives, around bias and fairness, where you have certain populations not properly represented in your training data, or you might have your metric end up overemphasizing one set of the population over another set. Okay, so and then of course, whenever you're training on models that involve human behavior, humans adapt. And as people adapt, you will also get bad actors. For example, imagine a model to identify toxic speech. The bad actors are going to basically recognize what your model does, and they're going to start to change it. So these are some of the common challenges in machine learning, and the patterns are all around addressing one or more aspects of these challenges. To just give you an idea, and because this is a TensorFlow meetup, I will focus a bit more on the development set of patterns rather than more on the production set of things. But let me just go ahead and pick a few of these 30 patterns and just talk about them. And let's start with a hashed feature. Okay, the basic idea is, suppose you have categorical features. How do you represent them? Let's say you basically have a machine learning model that needs to predict whether or not a flight is going to be late, right? It's predicting the probability that the flight is going to arrive late. And you have two input features. You have the departure delay, and you have the airport that the plane is departing from. Now, the departure delay is numeric, and you can directly put it into the model. But the airport, how do you represent the airport? Well, the most common thing that you do is that you one-hot encode it. Okay, but there are some problems with one-hot encoding a field like the airport code. Right, 3 problems. First problem is that of incomplete vocabulary. Right, suppose your categorical feature is a day of the week. Well, you have only 7 days of the week. Sunday, Monday, Tuesday, etc. So that is not a problem. Your vocabulary is complete. But what if your categorical feature is something like, say, the hospital ID? You're trying to predict a patient outcome, and obviously different hospitals have different cleanliness standards and different standards of care, and the quality of the physicians is different, etc. So you say, okay, I'm going to include the hospital ID and the physician ID as inputs into my ML model. At that point, it is going to be an incomplete vocabulary, because there is no way that you will have every possible hospital in your training data set. There's no, and that becomes a problem because what you've trained on, and when you go ahead and you predict it, what if you're trying to predict for a hospital that you did not have in your training data set, or a physician that you did not have in your training data set? That's a problem, right? The second problem is around the cardinality, the number of unique values that you have. Because remember, when you do one-hot encoding, if you have if you have a categorical variable with 7 possible values, the size of the one-hot encoded variable is 7, right? 7, 0, or 1s. So then, as the number of unique values grows, the size of your one-hot encoding representation becomes larger and larger and larger. So if you have 7 days of the week, it's no big deal. But suppose you have thousands or millions of unique values, now you run into memory issues, right? You run into problems around how big it is. So this is pretty common, right? We just talked about like a physician ID. You might have thousands of physicians in a city, and you want to basically go represent all of them, and that becomes problematic. So typically you run into cardinality issues with categorical variables in recommendation systems. For example, you're trying to recommend videos, you have thousands of videos. Or you're doing language models, you take every word, and the word is a categorical variable, and then when you represent it as a one-hot encoding thing, that becomes a problem. The third problem is cold start, which is kind of related to the incomplete vocabulary. Suppose you have a brand new physician who joins your system. You don't have any training data for them. So that now becomes a cold start problem. Again, cold start is very common in recommendation systems. You have a new user that you've signed up. Now you have a one-hot encoded value, and for that one-hot encoded value, you have no training data whatsoever. The thing to realize is that when you do one-hot encoding, and in a very simple, easy way to think about it is if you do a linear system, for example, every one-hot encoded value is independent of every other value. So one-hot encoding essentially assumes that all of your input categorical variables are independent of each other, which means that whenever you have a new data point, you have pretty much no way to deal with it. So you have to but at the same time, what we want is that we want some kind of a reasonable prediction to happen. So how do we do that? Well, the solution here, and this is the design pattern, is a hashed feature. The basic idea is you take something like the airport code and you say, I'm going to represent the airport code in a way that makes it unique. Fortunately, in the case of an airport code, we already have a 3-letter code like DFW for Dallas-Fort Worth that makes it unique. So you take that and then you apply a hash function to it. And the hash function basically gives you a number, right, for that 3-letter code. The number isn't unique. You could have the same hash for multiple of these, but it is over a very large space. And it is very, very, very well distributed. So it is, you can treat the output of the hash function as being uniformly distributed. So you get a sort of uniformly distributed hash function given the airport code. And then you basically bucket it. You take the modulo of that hash function and you decide the number of buckets. So let's say we have 4 buckets. Now DFW becomes that second bucket, and we one-hot encode just these 4 buckets. So the airport code DFW becomes the one-hot encode at 0100, right? So in other words, even though we may have hundreds of airports, we will only have 4 possible buckets that they get put in. So that's the idea of a hashed feature. And so how does this solve the problem, first of all, right? First of all, like just a quick implementation detail, you have to make sure that the hashing method, the hash function, that modulo is going to be the same in all languages, but the hash function could be different in different frameworks and different languages, etc. So you want to make sure that your hash function is repeatable, right? It doesn't have any random seed in it, for example. It's not you cannot use a cryptographic hash because cryptographic hashes have things like salts in them that make them not reproducible. So you have to make it reproducible, and you want to make it in such a way that it is the same. So that's why in TensorFlow, for example, you have a feature column method, categorical column with hash bucket. Or if you're using SQL, use something like a form fingerprint. Form fingerprint is a library that has implementations in C and Java and Python, etc., which means that no matter which language you use for your deployment infrastructure, you will have an implementation of the form fingerprint hash algorithm. So you take the form fingerprint, that is basically going to give you negative to positive. You take the modulo of it, and then basically you do the modulo in the number of buckets, and then you basically find the absolute value of that modulo. That gives you the number from 0 to 3 for 4 buckets, and that now you can now one-hot encode it. So as an example, right? So suppose you were to basically hash the code DTW. With 3 buckets, you will get the number 1. If you had 10 buckets, you would get the number 3. If you had 1,000 buckets, you would get the number 543. But remember that this is really the bucket number. It's a categorical variable. We're going to one-hot encode this. So we'll basically get a length of 1,000 in this case. So what you can also think about is that suppose, for example, you have 350 airports. If you hash them into 3 buckets, now you're basically putting an average 100 airports into the same bucket. So we're no longer treating the airports as independent. We're basically treating these 100 randomly chosen airports together. If you do 10, you have an average of about 35 airports per hash bucket because there are 350 airports. If you do 1,000 though, on average, right, every airport basically gets its own unique bucket. Right? It's not perfectly unique. There's going to be some bucket collision, but for the most part, you get it to be unique. So when you think about it, if your big problem is an incomplete vocabulary, hash the categorical variable into many more buckets than you actually have values for. And then the chances are that you will basically end up with a unique bucket per categorical variable. And it gives you the space to add new things as they come up. On the other hand, if your problem is high cardinality, you basically choose very few hash methods and very few buckets, and that way you kind of combine a bunch of these into the same bucket. Okay? So why does it work? If you have an out-of-vocabulary input, any input that you have will always be mapped to a known bucket. So if you have 347 airports, 10 buckets, you'll have an average of 35 airports per bucket. So you end up averaging it naturally. So it's not tied into a specific airport. And so what matters is now if you get a cold start problem, you get a brand new airport, it's going to go into one of those 10 buckets, and it's going to pick the prediction that you would have gotten for those 35 airports until there is enough unique data for this particular airport. Okay? So that's how you handle out of vocabularies. It also helps you with high cardinality because it doesn't matter how many unique input values you have. What matters is just the number of buckets. Of course, the bucket is lossy, but you've got to think that the alternative is you can't use a categorical variable at all. So rather than drop the physician ID, we get to at least use a lossy representation of it, right? And something is better than nothing is why we use the hashed feature. So what are some trade-offs here? Well, the trade-off is number one, there's bucket collision. So if as you increase the number of buckets, the number of entries per bucket goes down, the collision probability goes down. But you should remember that there is always the chance that there is going to be some bucket with collision. In fact, that probability is higher than you think. Even if you have only 347 airports and you use 100,000 buckets, there is a 45% chance that there is one bucket with more than one airport in it. Okay, so there is going to be bucket collision. But for the most part, right, when you do 100,000 buckets, each airport will get its own. But there is a probability that it's going to have something. One of the big problems here is of skew, right? So O'Hare in Chicago is one of the busiest airports in the world. So imagine the hash bucket that contains ORD. Okay, so now let's say we have 100 hash buckets. Okay, and we base now on average there are going to be 3 airports per hash bucket. This happens to be the 3 airports that share the same hash bucket as O'Hare. There are like 3.6 million flights from O'Hare and only 66,000 flights from Burlington, Vermont. So what's going to happen is that this bucket is going to take on the characteristics of O'Hare because there's so much data from O'Hare. What this means is that the model is going to think that Burlington, Vermont, taxi times are going to be long because O'Hare's taxi times are going to be long. And that's going to be a problem. So the way that you deal with this is that you try to also add aggregate features. So whenever you have a hashed feature, also add an aggregate feature. For example, find the average taxiing delay at the airport, and that's just a numeric variable. Add that. So add that as a specific new input into your ML model. Now, there's another alternative, which is like, if you have 100,000 buckets, many of the buckets will be empty. And now if you have an empty bucket, you have a huge problem. The model is going to start to overfit because now it's empty. It can assign any kind of weight it wants. And so what you have to do is that you have to also add in L2 regularization. So whenever you do hashed features, use them with aggregate features, use them with L2 regularization. So this gives you a pretty good idea of how we approach design patterns in the book, right? We basically start off with the problem statement, right? This is a problem statement. We say this is what you would typically do. There's a problem with it in some situations. We present a solution. So this is one approach to do it. We talk about implementation details of that solution. We talk about why that solution works. And then we talk about things to keep in mind if you apply the solution, right? Trade-offs and alternatives for that. And again, so there's like 30 patterns. I'm not going to be able to go through all of them. So let me go ahead and pick another one that might be kind of interesting to this group. Let's pick maybe, which one? Let's see. Okay, let's pick number 23, bridged schema. Let's go all the way off. Okay, so this is going to be quite a bit away. We'll just escape this. Go down to 23. I will basically do that, and then I'll open it up for questions, and we can just do a discussion after that. So this deck is a work in progress. So that's why I had to pick one that I know that we had the slides already built for. So bridge schema, okay? So here's a problem here, okay? Suppose you've trained a machine learning model that predicts the amount of the tip, right? So you have a bill. I know you're in Europe, you guys don't do tips, but let's assume that you're basically doing tips, and you have a delivery, and you want to basically recommend how much of a tip to provide to the person who delivers your food. Okay. Now, in order to do this prediction, you take the payment type as an input. The payment type used to be cash or card, and it turns out that when you pay with cash, people tip round numbers like $1, $2, $3. When they pay with a card, they basically pay specific numbers. So you would have different recommendations based on whether it's a cash or a card. So that was your input to your ML model to predict the tip. Now, after you've rolled this out, it turns out that you've improved your prediction system. So where originally all you knew that it was that it was a card, a credit card, now you know whether it's a credit card, whether it's a gift card, or whether it's a debit card. So you have more. So that original category of cards basically is now 3 potential values: credit, gift card, or debit card. And this is a very, very, very common scenario, because after you roll a machine learning model into production, your input data is going to get better. Your input data is going to get better because the people who provide you that input data are constantly improving their systems. And so you're going to get better data. So your original data that was I just tell you that it's a card. Now I can tell you that it's a credit card, a gift card, or a debit card. Now, you obviously want to use this new information as quickly as possible. Why? Because your payment system has been upgraded. So all of your new transactions have this new information. But you need 1 million transactions to train the model, right? You train the model before 1 million transactions. You need 1 million transactions. It's going to take you many months to get 1 million transactions. You don't want to wait that long. So the question is, how can I get started as quickly as possible with the new data? Because again, during prediction time, you always have the new information. So you want to use it. You don't want to wait until you get 1 million transactions to train a new model. Now, what do we have? We have 1 million transactions with the old schema, which is cash versus card. And we have 5,000 transactions with the new schema. Question is this enough? Can I get started with just 5,000 by somehow taking advantage of 1 million older schema transactions? Okay. The approach is to basically, that's a bridged schema approach. The first thing is you estimate the distribution, right? So you look at the 5,000 new transactions and you say, how many of these credit card transactions, how many of the card transactions were gift cards, debit cards, or credit cards? So let's say 10% were gift cards, 30% were debit cards, and 60% are credit cards. So you know that it is 10, 1:3:6 is the distribution among the 5,000. Given that, now you do data augmentation on your old examples. Okay, so I'm going to show you two approaches. We're actually going to use a second approach, but it's a lot more understandable if I show you the first approach, which is a probabilistic approach. So the idea is that if the type is cash, we just pass it through. Cash is cash. But in your older data, if the type is a card, then we generate a random number, right? We generate a random number and we throw a dart. And if that random number is like 10% of the time, we choose a gift card, 30% of the time, we choose a debit card, and 60% of the time, we choose a credit card. That's pretty much our data augmentation. And then we train the model, right? So we train the model. So we've now taken the old data and we basically, some of the time we're doing 10%, some of the time we're doing this. So the idea is that if you train enough epochs, then every card transaction, 10% of the time will be treated as a gift card, 30% of the time it will be treated as a debit card, and 60% of the time it will be treated as a credit card. Without any more additional information, that's kind of the best that you can do. And so we do this data augmentation on the old examples to basically deal with this. Now, once you've understood that, the static becomes very, very, very clear. What are we doing when we do static? We say if we train long enough, it is just as if we take any card transaction and we quote unquote one-hot encode it, except that so now we one-hot encoded multiple times. So 10% of the time it will be this one, 30% of the time it will be this one, 60% of the time it will be that one. So rather than run through this model so many epochs, we just average how this particular example is going to get seen. And that's now the way that we represent this old value. So now we just go through our 1 million old examples and we replace the old example, that each card transaction, by something like this. So the 0 here is cash. This is your gift card. This is your debit card. And this is your credit card. So we just replace it with this value. So it's not one-hot encoded, but it's the average of what the one-hot encoded values would be if you apply the probabilistic approach to data augmentation. So once you do this, we can go ahead, but we need to answer two questions. Number one, how do we measure performance? Is this going to really work? And secondly, how many old examples do we need to pull in order to do the data augmentation? Do we need to use all 1 million, or can we use fewer ones? So first of all, to find we need to find the number of evaluation examples. Okay, so remember that we have to always evaluate on the new data, right? This is the new data with the true card categorization. That's what you evaluate on. But we need to find out how many of those we need. So what we do is that we basically go to this old data set and we basically do subsets. We pull subsets of different sizes and we look at the variability of the evaluation. And again, the book goes into a lot more detail of exactly how you do this, and the GitHub repository has code to show you how to do it. But it turns out that if you change the evaluation size, the variance will drop and it'll start to plateau. So it looks like this one is plateauing between about 2,000 and 3,000. So let's say at 2,500 is what we need. So we have 5,000 new examples. We need to keep 2,500 of them for evaluation. We'll use the remaining 2,500 for training. And then once you have that 2,500, we need to find the total number of older examples that we need. And again, we do that evaluation metric and we look at where it plateaus. And it turns out that you need about 20,000 older examples. So now you know you need 20,000 old examples, 2,500 new examples. You put that in, you train the model, and it goes on. So what are some alternatives here? Well, you might say you can do a union of the two. You can do the one-hot encoding, and you can do the the original one. That kind of works with data warehousing when you're changing from one schema to the other schema, but it doesn't work in machine learning because all your predictions are always the new one. There's another pattern called the Cascade Pattern where you train multiple models one after the other, but that is way too complex. And we don't suggest it because this one, remember, is a temporary workaround. It's only until you have enough new data. Once you have enough new data, you will stop using any older examples. You will train exclusively on the new examples. Okay. And if the feature is not categorical and if it's not mutually exclusive, what do we do? Well, if you have new features that are not categorical, if it is numeric, then you can use the mean value if it's normally distributed. If it is, use the median value if it is skewed. Use the median if it is sortable. Use the mode if it is not sortable. Use the frequency if it is Boolean. Again, I won't go into the details of why this is what you do for these different situations. But again, we discuss this in the book. We talk about why these recommendations work for non-categorical features. So the bottom line is you can bridge your schema, right? So bridge schema is useful whenever an input provider makes improvements to the data feed. It allows you to use as much of the newer data as is available, but to do data augmentation with some of the older data to improve your model accuracy. Okay. And with that, I'll go ahead and I've now talked for about 40 minutes. We talked about 2 design patterns. So hopefully this gives you a good idea of what the book is about. And I will start to take questions now.
All right. Thanks a lot, Lak, for the interesting discussion already. There we go. So we have our first question popping up from Victor, which is, can we use this hashing function in Bigquery?
Absolutely. Okay. Victor asks, can we use the hashing function in Bigquery? Yes. In fact, the SQL I showed you with the form fingerprint is Bigquery SQL. So yes, you can use that. Just put that into the transform clause of your Bigquery query, and then it will be repeated in prediction as well. So that makes it very, 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 very convenient. Like Bigquery allows you to do this, save the transforms that you do during training and repeat them in prediction. And yes, so there is the form fingerprint is how you hash. Again, very, very, very important. Do not use the Java hash function or the Python hash function because they will not be repeatable, right? So do not use a SQL hash function either because they will not be repeatable. Use something like the form fingerprint that has the same implementation in multiple languages.
And maybe a link to that as well, because for people who are not aware of Bigquery, you also have Bigquery ML. Maybe if you can
Bigquery form fingerprint. There we go. Okay. So that's your form fingerprint function that shows you how to use it. And there we go. Right. Any other questions? Victor again. Okay. When dealing with hash buckets queue, does it make sense to try and use a hash function that takes into account feature similarity? So similar airports end up close to each other. So Victor, that you have the exact correct intuition here. The answer to that is to use an embedding, Okay, so not to use a hashed feature, but to use an embedding column. So yeah, so when closeness is important, use embeddings. When out of vocabulary is important, use hash features. And if both of these are important, then exactly what you're suggesting, you can use the two in combination. Use a hashed feature with like 100,000 buckets, and then pass them through an embedding layer, and that gets you the closeness things. So you can use hashed feature and embeddings together. So that's the two patterns that I would use if you want to get that closeness relationship as well.
All right. So in case somebody else has questions, please put them in the chat so I can also share them. Maybe in the meantime, because you mentioned Bigquery, so I'm assuming not everybody is familiar with Bigquery, of course.
Right.
You also have Bigquery ML, and you have TensorFlow, so it might be good if you can give like...
Yeah, absolutely. So Bigquery ML, Bigquery is the data warehouse on Google Cloud. Okay, so and basically it has a number of machine learning models that are already built in. So as an example, right, this is how you would normally write your SQL query. You say, I want to select a user ID, an item ID, and a rating from my table. To train a matrix factorization model, you would basically add a SQL statement at the top saying, I want to create a model. The model type is matrix factorization, and the user column is this, and the item column is this. Here's the L2 regularization that I want, and this is how many factors, right? So when you do matrix factorization, you kind of decide you're going to take all your millions of videos or millions of users, and you want to represent them in how many user factors are item factors. So you specify that factors, and that's pretty much it. So this is really, really, really cool because you're doing your training without ever moving your data out of your data warehouse. And there's a number of machine learning models that are built into Bigquery ML. So actually, maybe if we can just look at the create model, that should tell us so you basically have AutoML classification for any kind of classifier, AutoML regressor. So this will go ahead and try a family of models with neural architecture search, pick the best one. You can do XGBoost, you can do deep neural nets, you can do linear regression, you can do k-means, right? So there's a number of different models k-means, logistic regression, linear regression. You can also load in a TensorFlow model. So you can train a TensorFlow model, load it into Bigquery, and use Bigquery for predictions. You can train a Bigquery ML model, and you can export it as TensorFlow. So these are actually very interoperable, right? So what Bigquery ML does is that it actually trains a TensorFlow model, right? So underneath the seams, it's using SQL, but it's training a TensorFlow model. And so you basically get a TensorFlow model that you can export out, and you can go use it in TensorFlow predictions. So if you want to train in Bigquery ML and deploy in TensorFlow, you can do that. If you want to train in Bigquery and if you want to train in TensorFlow and do batch predictions in Bigquery, you can do that as well. Okay. Any other questions? Okay. Do you have a favorite design pattern, and why? I don't know. Probably my favorite design pattern is one of the simplest, but one of the most powerful, which is a stateless serving function. Serving functions are extremely, extremely powerful. And there's so many things that you can do with serving functions. You can add a lot of indirection to them to provide amazing capabilities and amazing scale. So to me, the stateless serving function is probably the one that I would go for if you'd say, like, what is your the kind of key nice function? And talking about serving functions, we have a new book that actually just came about in early release, Practical ML Vision book, O'Reilly. Let me see if I can find it. Early release, because it was just today. Practical. Oh, okay. It's not yet indexed in Google search, looks like. Okay, practical machine learning. Okay, let's just see if Ali. Yeah, I'll try to find it. Media search for machine learning vision. There we go. Okay, so literally we came out today. This book has a huge chapter basically on all of the tricks that you can do with serving functions to basically do a variety of really neat things around images, including like adding things like explainability along with the image predictions using a serving function. So as an example of the kind of really powerful kinds of things that you can do with serving functions, this book basically, it's an early release now, but it should be out pretty soon. It talks about many of the things that you can do. Do you have recommendations on how to get started with TFX? Haha. Okay. So TFX, for everyone out there, is TensorFlow Extended. It basically gives you a very prescriptive pipelining system for training, evaluating, and deploying ML models. Okay, so it's basically very, 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 very prescriptive and says like, normally you will do data validation, and then you will do pre-processing, and then you will do training, and then you will do evaluation, and then you will do deployment, and then it gives you a number of operators for each one of these. So that is really very, very, very well thought out and put together if you are training structured data models. Okay, for structured data models, TFX is like extremely good. A good way to get started is a book by Hannes Hapke on, I think, production ML pipelines, something like that. Building ML pipelines. Yeah. So this is a good book by Hannes, and it is about TFX. Okay, so this is about building machine learning pipelines with TFX. So this is how I would suggest that you get started. It talks about how to develop with TFX and how to deploy with TFX. And TFX has a pretty steep learning curve. So like Hannes's book, it's a very slim, nice, very concise volume. So I strongly suggest it. Will you keep updating the collection of ML design patterns with more patterns? We don't know, right? So I guess there's something that we discussed a little bit, and we said, look, if these things, there's like more of these that we start to see, we might basically go ahead and write blog posts about them and link them from the GitHub repository. And then once we get to maybe about 10 or 15, maybe we might like talk to O'Reilly, but the book is long enough already. So I don't know if adding it in the book is an option, but definitely adding links from the GitHub repository should be possible. And as we see, again, these design patterns are things that we notice people doing, really neat ideas and best practices. And if we find them, we will basically write an article about them and link them from the GitHub repository. Can you recommend a good way to encode geographic XY coordinates for ML models? Yes. If you're going to be geographic XY coordinates, use this thing called a geohash, right? So geohash is basically a way in which you can basically take any coordinate pair, okay, and basically you will get a string, and that string basically captures closeness relationships. So you want to use a geohash, right? So that's the best way to do locations. Okay, so as an example, so let's see. Our Bigquery book had an example of doing a geohash too. Again, you don't need to use Bigquery to do a geohash. There are libraries in other languages as well, but I'm just going to show you what that geohash looks like. geohash. Okay, so for example, when you take this longitude and latitude, you get this string, and that's the geohash. The cool thing about this string is that it's not just a string. The letters on the string, right? All of the geohashes that start with C22YZ are all close to each other. So every additional letter adds an additional resolution to it. So when we say 10, you basically get 10 of these letters. If we had said 5, you would have gotten just these 5 letters. Okay, and that's the way in which you basically get closeness relationships. So for locations, I really suggest using geohash. So it is like an image hash. Yes, exactly. It is kind of like an image hash. It basically captures that closeness relationship between, it's like an embedding, right? And if you think about sort of like that, it captures that closeness relationship between two lat-longs. Otherwise, imagine that you have a longitude like this, and you have another longitude that's minus 121 and 46. Right? You want those two that are very, very close to each other. They're less than 100 kilometers apart, and you want them to have very similar geohashes. And geohash will give you that. Any other way that you do it will not, because they will be in two. Even if you, like, say, you do you bucket them, you make them into a grid, they will be in two different cells. And these cells themselves will be independent of each other. So it doesn't give you the nice benefits that a geohash does. Again, big lesson is not to reinvent the wheel, but to basically now, this is all research that's been done. No, it's out there. So Thomas, the great question, right? That this idea that there's probably something out there that solves my problem. That's a good approach to take, because the naive way to do it would be to basically just discretize the latitudes and longitudes. It's not as good as a geohash. So just the fact that you asked the question is actually pretty good, right? That's a great attitude, because that helps you discover these answers that you might not have known existed. Are you aware of any ML design anti-patterns or some pitfalls to look out for when trying to apply the ML design patterns? Pretty much every one of the design patterns has a trade-off section, because none of them are free, right? Like when I talked about the hash feature, I said you're going to get bucket collision. Okay, that's a trade-off that you're willing to make. So the second part, are there pitfalls? Yes, absolutely. Every single one of them has pitfalls. And so you want to be aware of them. Am I aware of any ML design anti-patterns? I've not seen anybody basically talk about things that you should avoid. Well, that maybe there's a chance for somebody to catalog them.
All right. Thanks. I think for now all the questions have been asked, but please share if you have any others. Maybe a question from my side. So you were with 3 authors, and you came up with 30 design patterns. So I was interested a bit, like, how do you end up with those 30? Is it like you already had your ideas before, or because I really like the interactivity as well, and like the way to get to that point.
Right, absolutely. So the way this started was that I wrote a set of Medium posts. Okay, so there it is, right? So I wrote a few Medium articles on the design patterns, like about 5 of them, I think, and basically got a lot of feedback on how these were useful ways to think about these patterns. And the reason about that I did this was because it was a TensorFlow meetup, and at the time that I wrote this, I was working with the Keras team. The Keras was coming out, which is feature column library. And so this was something that I was interested in, and I wrote it. And when I was trying to say, how do I explain this? It became like, maybe I shouldn't just talk about a transform. I should talk about why it's important, right? And so that's how the design pattern lens came about. And I did a few talks on the topic as well, and saw that there was actually a difference. Whenever I did the articles, people were really interested in how am I going to implement it, what are the trade-offs and everything. Whenever I did a talk, people were really interested in, I didn't even realize that this was a problem before, right? I thought that the only way to deal with categorical variables is to one-hot encode them. I didn't realize that we had these others. So that's when I kind of realized that there's an audience for having a much more complete explanation. Here are some problems that you're going to run into, and this is how you would implement them. Here are the trade-offs, things to think about. And with that, I wrote a book proposal to O'Reilly, and they were interested. And at that's when I basically looped in Sarah and Michael and said, no, let's go ahead and ask them if they were willing to join me in writing the book, because I only had 5 at the time, and I knew that we needed to write. I had a list of about 20, and then as we kind of discussed and hashed it out, and we started looking at projects that were like successful large projects in ML. We identified a few others. It became a total of 30, and then the 3 of us, we split them. So every chapter, we would just split the patterns, and we would basically write them and then review each other's work, and then send it off to our colleagues, have them review it. And then once that was all done, then we basically sent it to O'Reilly. So it was a process.
All right, thanks. That's interesting. In the meantime, we already have a next question. There we go.
Okay. Would you recommend Bigquery ML for an ML production deployment? Well, when you say production deployment, there are 2 potential ways you can deploy it. You can deploy it for batch predictions, or you can deploy it for online predictions. For batch predictions, I strongly recommend Bigquery ML, right? It's amazingly scalable. So for example, if you want to basically create a set of recommended items for all of your users once a day, Bigquery ML is like the most scalable, most inexpensive way to do it. I totally recommend that. On the other hand, if you want to do online predictions, Bigquery, right, is a data warehouse. It tends to have about a 1 to 2 second latency for any query, which basically means that it's not great for online predictions. So for online predictions, I would train it in Bigquery ML because it's so easy. But then I would export it as a TensorFlow model and then use TensorFlow serving to deploy it. But if the question is Bigquery ML good enough? And as you saw, we have AutoML, we have deep neural nets. There's more coming, which means that for now, we have very sophisticated recommendation systems, hybrid ML models that you can train with just Bigquery ML. So you're not making any compromises. So let's see, hybrid machine learning recommendation model. ML. Yeah. So yeah, this is somewhere here. Okay. Yeah. Okay. So this one just talks about the matrix factorization, but the Bigquery book. Bigquery. Book. Okay. So this book has its chapter 9, I think. Yeah, the BQML. This is from the Bigquery book. It actually has a hybrid machine learning model that basically trains a combination of a deep neural net and a matrix factorization model. And in practice, this is as good as pretty much like any other recommendation model that you would train anywhere else. So you're not making any compromises on accuracy these days when you use Bigquery ML. So strongly do recommend it. But with the caveat that I talked about, is that you would not use it for online predictions. You would use it for batch predictions. For online predictions, you should export the model as TensorFlow. What is the expected release date for our new book, Practical ML for Computer Vision? Will it contain any of the design patterns mentioned in the last book? So these are different books. So we do mention the design patterns here and there, but primarily the computer vision book is around doing really sophisticated image computer vision models, how to do counting, how to do object segmentation, how to do image captioning, how to do GANs. That's basically what the book is about. The book is about from simple to hard problems that you can solve using computer vision and images. So there are design patterns here and there, like I talked about with stateless serving. That's a big part of the book. There's an entire chapter that basically takes advantage of serving patterns, but that's not what it is. What is the expected release date of the book? Officially, it is October, but in practice, these books tend to come out about a month to 2 months earlier than that. So I think by July, you should probably start to be able to see it. Just follow me on Twitter. I'll be sure to post when the book is out.
Right, and I think maybe this one is a potential anti-pattern, right? I think the over-engineering aspect sometimes of doing an ML project would be my number one pick as an anti-pattern. I assume it's also something that a lot of people are familiar with.
Correct. Yeah. So this would be this. Now here we're training two models and we're putting them together. But the way that we are doing this is something we talk about in the book. Is that when you have something as complex as this, you can use an ML pipeline with a cascade to make it all a single model. To as you said, Matthias, to avoid like dinking around and doing them separately, in which case you will run into a lot of errors. So there are ways to even train multiple models as a cascade, but to do them in a repeatable way.
All right. I think for now, we had all the questions answered. So I want to thank you again for this great presentation. And then, I think we can finish unless you have some closing notes to share from your side.
I don't have any closing notes. I know I had a lot of fun. It was like great questions today. So thank you all very much. Okay, so I don't think I have any closing notes here. Yeah.
All right. Yes. Great. Well, thank you all. And then, let's see each other in the next meetup.
Okay. So that's, I'll leave you with some links. So that's the book. That's the two of us. Michael is not on social media, but follow Sarah and me on Twitter. We both write blogs. So those are links to the blogs. Okay. And thank you all very much. And thanks, Matthias, for putting this together. It was awesome.
Thank you.